3 or 4, you should be able to manage on your own. In question 1, you are given that a cable has a capacitance of 2135 picofarads per 33 meter length and 11.38 microhenries of inductor for the same 33 meter length, and you are supposed to determine the characteristic impedance Z0 and the propagation constant gamma. Of course, we are not given a frequency, so it means that gamma will be in terms of omega. Now, as solution, we have our Z0 being given by square root of, between brackets, R plus j omega L over G plus j omega C, while gamma is the square root of, between brackets, R plus j omega L into, between brackets, G plus j omega C. But you know, we are not given R and G, so we make the assumption that R is equal to 0 and G is equal to 0. Therefore, Z0 is equal to square root of R plus j omega L over G plus over, Z0 then becomes square root of j omega L over j omega C, because R is 0 and G is 0. And when you remove omega, the two omegas, j omegas cancel, therefore Z0 is square root of LC. And of course, our gamma becomes equal to j omega square root of LC. Now, therefore, our Z0 is equal to square root. Now, our L is 11.38 times 10 to the minus 6 over 33. That gives us the inductance per meter. And our capacitance C is 2135 times 10 to the minus 12 over 33, which gives us the capacitance per meter. And therefore, our Z0 is equal to 73.01 ohms. Just note that for a lossless line, the characteristic impedance is real. Similarly, our gamma is j omega square root of LC. Now we insert the values of L and C as before, where we've divided the given value by 33 meters in each case. And therefore, gamma is j omega 4.72 times 10 to the minus 9 per meter. So those are the solutions for Z0 and gamma in this particular problem. Now here we have taken question 3 and 4 and solved them together. We are given that a telephone line has a value of R given by 30 ohms per kilometer, L is equal to 100 millihenries per kilometer, G is equal to 0, and C is equal to 20 microfarads per kilometer. Now, at a frequency of 1 kilohertz, which typically was the band of the telephony line, remember, a typical telephony line would operate from about 300 hertz to 3.4 kilohertz. So 1 kilohertz would be somewhere in the center of the voice band. So at 1 kilohertz, you are supposed to obtain the characteristic impedance Z0, the phase constant beta, and the attenuation constant alpha. Now to solve this, we have the standard expressions for Z0 and gamma as shown. Now our frequency, of course, is given as 1000 hertz because that's 1 kilohertz. R is 30 ohms per kilometer, which is 0.03 ohms per meter. G is equal to 0. C is equal to 20 times 10 to the minus 6 farads per kilometer, which is 20 times 10 to the minus 9 farads per meter. L is equal to 100 millihenries per kilometer, which is 100 microhenries or 100 times 10 to the minus 6 henries per meter. Now, Z0 squared is equal to R plus j omega L over G plus j omega C. Now, when we insert the values of R, L, G, and C with omega given by 2 pi f, we have the expression there for Z0 squared. And therefore, when we calculate that, we find that our Z0 squared is equal to 5006.5, and the angle is minus 2.7 degrees. And therefore our Z0, which is the square root of Z0 squared, is equal to 70.76, and the angle is minus 1.35 degrees. Remember, for a complex number, when you get its square root, you get the square root of the magnitude, and the angle is simply half of what it was before. Okay, so the square root of 5006.5 is 70.76, while the angle, which was minus 2.7, now becomes here, when you take the square root, minus 1.35 degrees. Now, so that is our characteristic impedance Z0. Now our gamma squared, again we have that expression, which is r plus j omega L into g plus j omega C. And when we expand this, we find that our gamma squared is 7.91 times 10 to the minus 5, and the angle is 177.3 degrees. And therefore our gamma, which is alpha plus j beta, simply the square root of gamma squared, which is 8.89 times 10 to the minus 3, and the angle is 88.65 degrees. Therefore our alpha is the real part of gamma, which is 8.89 times 10 to the minus 3 cosine of 88.65, and that gives us 2.1 times 10 to the minus 4 nepers per meter. Now our beta is simply the imaginary part of gamma, which is 8.89 times 10 to the minus 3 sine of 88.65 degrees, and that gives us 8.89 times 10 to the minus 3 radians per meter. So that's solution for both question 3 and question 4. Now there's another typical problem you'll encounter for in transmission lines. You are given the characteristic impedance at 500 megahertz. You are given that Z0 is 80 ohms, alpha is 0.04 nepers per meter, beta is 1.5 radians per meter, and we are required to determine the primary line parameters R, L, G, and C. Now, we go back to the standard transmission line equations. Our Z0 is given by that, and our gamma is given by that, which is alpha plus j beta. Now, if you multiply Z0 by gamma, which is Z0 into alpha plus j beta, then you get R plus j omega L. Z0 times gamma simply gives you R plus j omega L. Now, it therefore means that the real part of Z0 times gamma is alpha times Z0, which in this case is 0.04 times 80, which is 3.2 ohms per meter. Now, when you look at the imaginary part, which is omega L, that gives us Z0 times beta, and therefore L is beta Z0 over omega. And when you calculate that, you find that your L is 3.82 times 10 to the minus 8 henries per meter, or 38.2 times 10 to the minus 9 henries per meter. Now, the second part, to get our G and C, we notice that gamma over Z0 is equal to alpha plus j beta over Z0, which is given by G plus j omega C. You can confirm that from the equations. And therefore your G is simply the real part of gamma over Z0, which is 0.04 over 80, which is 5 times 10 to the minus 4 Siemens per meter. Now omega C is the imaginary part of gamma over Z0, which is equal to beta over Z0, and that is 1.5 over 80, and therefore C is simply 1.5 over 80 divided by omega. And therefore from there you find that your C is 5.966 times 10 to the minus 12 farads per meter. Now in question number 7, we are told that a distortionless line has Z0 equal to 60 ohms, alpha is 20 millinepers per meter, which is 20 times 10 to the minus 3 nepers per meter, and the first velocity u is equal to 0.6 c, where c is the speed of light in a vacuum, which is standard, well known. Now you are supposed to find r, l, g, c, and lambda at 100 megahertz. Now, I just want to say something about lambda. Lambda in a guided medium is different from lambda in free space. In a guided medium, lambda is determined by the phase velocity, and therefore lambda is a function of beta, because remember, phase velocity is omega over beta. Okay, so let's go ahead and calculate. This line is distortionless, so we have the standard equation for a distortionless line. Your z naught is square root of r over g, and your alpha is square root of rg, and therefore r is alpha times z naught, and that therefore is your alpha is 20 times 10 to the minus 3, and z naught is 60, and therefore you find that your r is 1.2 ohms per meter. Now your g is alpha over z naught. Now alpha over z naught is 20 times 10 to the minus 3 over 60, which is equal to 3.33 times 10 to the minus 4 Siemens per meter. Now, our first velocity is omega over beta, which implies that beta is equal to omega over first velocity. Now, our first velocity is 0.6 times the speed of light, which is 0.6 times 3 times 10 to the 8. Therefore, our beta is 3.49 radians per meter. Remember, our omega is 2 pi times 100 times 10 to the 6. Now, we also are given that our z naught is 60, but we know that our z naught is equal to square root of L over C, while for a distortionless line, beta is equal to omega root LC. Remember, z naught is square root of R over G, which is the same as square root of L over C, because for a distortionless line, R over G is equal to L over C. And therefore, when you multiply beta with z naught over omega, you get your L, and therefore your L then becomes 3.33 times 10 to the minus 7 henries per meter. Now, your capacitance is beta over omega z naught, which is equal to 3.49 over 60 times 2 pi times 100 times 10 to the 6, that is 100 megahertz, which is 9.26 times 10 to the minus 11 farads, or 92.6 picofarads per meter. Now, your guided wavelength, lambda, and that's what is being asked for here, is 2 pi over beta. Remember, beta determines the phase velocity, because phase velocity is omega over beta. We've seen that before. And therefore, beta has been determined from the phase velocity, and therefore lambda is 2 pi over beta, which in this case is 1.8 meters, because it's 2 pi over 3.49. And that gives us 1.8 meters. So that is the wavelength within the transmission line. We call that the guided wavelength. That is different from free space wavelength. Now finally, in question 9, you are told that a coaxial line of length 5.6 meters has distributed parameters R is equal to 6.5 ohms per meter, L is 3.4 microhenries per meter, G is equal to 8.4 millisiemens per meter, and C is equal to 21.5 picofarads per meter. Now, if the line operates at 2 megahertz, calculate the characteristic impedance and the end-to-end transmission delay. Let me just say something small about end-to-end delay. You see, a signal enters the coaxial line at one point and it exits 5.6 meters later. which means it has to travel over a distance of 5.6 meters. That is where the delay comes from. And to determine that delay, we'll have to get the phase velocity of the wave inside this particular medium. And of course, from the phase velocity, we'll be able, from the length, we should be able to get the delay in seconds. Okay, so first of all, we have to determine the characteristic impedance, which is standard, given by Z naught is equal to square root of R plus j omega L over, between brackets, G plus j omega C. Now we get Z naught squared as before, and when we insert the values of R and G and L and C, with omega given by 2 pi times 2 times 10 to the 6, because 2 times 10 to the 6 is your frequency, then Z naught squared is equal to 160.1, and the angle is minus 6.87 degrees. Therefore, Z naught is the square root of Z naught squared, and that gives us 12.65, and the angle is minus 3.44 degrees ohms. So just notice that generally Z naught is not real. So Z naught in general is complex, which means it has a magnitude and a phase angle which is non-zero, unless the line is lossless. Now, to get beta, we notice that your gamma squared is equal to R plus j omega L into G plus j omega C. We need this in order to calculate beta, but we will also calculate alpha, though it's not necessary here, because all we need is to determine the end-to-end transmission delay. But also we want to get an indication of the attenuation over the line. So we have gamma squared. When we insert the values of R, L, G, and C, and omega, we find that our gamma squared is 11.67, and the angle is 169.57 degrees. And therefore, our gamma, which is alpha plus j beta, is square root of gamma squared, which is 3.416, and the angle is 84.79 degrees per meter. Normally, gamma is given in per meter. Now, alpha is simply the real part of gamma, and therefore is 3.416 cosine of that angle, 84.79 degrees, and that gives us 0.31 nepers per meter. While beta, which is the imaginary part of gamma, is given by 3.416 sine of that angle, 84.79 degrees, which is 3.40 radians per meter. Now, therefore, our phase velocity is omega over beta. Now, our omega is 2 pi times the frequency, which is 2 times 10 to the 6, that's 2 megahertz, and you divide this by beta, which is 3.4, and that gives you 3.7 times 10 to the 6 meters per second. So that is the velocity of the signal in this particular line. And therefore, the delay, the end-to-end transmission delay, the delay experienced by the signal as it travels over this cable of 5.6 meters is simply given by the length of the cable divided by the phase velocity. And that gives us a delay of 1.515 times 10 to the minus 6 seconds, or 1.515 microseconds. Thank you very much, class. You should be able to do the other tutorial questions. They are fairly easy. And I wish you well with your test number 1 on Friday between 11:20 and 12:20.